Okay, so in the last lesson, we learned two things about continuous random variables. We learned that we cannot assign probabilities to individual outcomes. No probability x equals 3 or anything like that. Okay, we can assign probabilities to intervals. Okay, so the probability that x was between C and D is the area under the PDF between C and D. And we actually do have a function that assigns probabilities in this way. Okay, so, and that is, surprise, surprise, the CDF. Okay, so what does that stand for? That is the cumulative distribution function. That's how you get CDF of random variable x is the probability. I'm just going to write this, and I'll talk through the little bits. So capital F of x, it's the probability that x, this is again capital letter random variable, x is less than or equal to b, and that is area under the PDF, little f of x, the PDF of x, between negative infinity and b. Okay, let's think about that, what we're doing here. So if I've got something like that, that could be PDF here. And it's a PDF as long as the total area under the PDF is 1. And for that to be true, it's got to be, the ends have to be approaching 0 at some point. So I'm hoping you'll use your imagination and accept that. What we're looking for here is the probability that random variable x takes a value less than b. So let's put that in here with a different color. Okay, so that is the area here. And what I've shaded here in purple is indeed all of these things. It is the probability that x is less than b. It is the integral from negative infinity, so as far small as x can possibly go, up to b. B is the upper limit of integration here. And what I'm integrating here is the PDF. Okay, so what I'm integrating is the PDF and the variable, the function that I get, the antiderivative function, the area function, that is the CDF. Okay, so that's consistent with everything we know about integrals, that they give us areas under curvy functions. I like to use, and I'm not the only person who does this, I like to use a different letter, B, here as the argument of the CDF, because it's helpful to me when I'm working through the details to keep straight the value of x whose probability we want. Okay, that's my B. And the fact that x is the variable that we are integrating with respect to. You don't have to do it that way. If you want to use x in both places, you can, but then you find yourself, if you are actually evaluating the definite integral, saying things like, well, it's let x go from x to 0, and that's too many x's for me. So to me, it's somewhat helpful to keep the number whose cumulative probability we are seeking, the number B where we're looking for the probability that the random variable is less than or equal to B. Okay, so it's the critical value, the value we're plugging into the function and getting a probability here, keeping that distinct from the variable that we're integrating the PDF with respect to. But again, I want to emphasize that other part. Capital F of X really does give us a probability. Remember, I was kind of hammering on that in the last lesson, that PDFs, you plug a value for X into a PDF, you get the height of the density function. You do get a number, but that number is not a probability. You integrate that PDF over some specific range so that and that's the equivalent of plugging a number into your capital F here. That number really is a probability, but it is a cumulative probability. It's not the probability that X equals B, it's the probability that X is less than or equal to B. Okay. And yeah, so some other things I want to say about CDFs here. If we want a closed interval, okay, so this probability that X is between C and D, that's just going to be the integral from C to D of PDF with respect to X. And that, again, sort of remembering how we evaluate definite integrals, that is the CDF evaluated at D minus the CDF evaluated at C. Okay, so if we're doing a similar picture here, we've got C and D, and we've got our PDF X here. What we're doing is we're finding the area, the total area under the curve below D, and then we're subtracting off the area below C, and so what we're left with is the area in between. Yeah, that's true for any kind of integral there. Okay. A couple of other points about CDFs. CDFs. Okay, one is that one way in which continuous random variables are actually simpler and easier to work with than discrete random variables is we don't have to worry about edge cases. Okay, so for continuous random variable, the probability that X is weakly less than A is the same as the probability that X is less than or equal to A. So you really don't need to worry about whether we have strict inequality or a weak inequality there. And of course, that's because we're not assigning any probability to the individual outcomes. Okay, we might say that those individual outcomes have measure 0, they have no probability assigned to them. They don't make a difference. There's no area assigned above a point. You have to have an interval in order to actually get some area, get some probability assigned to it. Okay, some other things that I'm going to illustrate in the next couple of videos, but I'll just comment on them here about CDFs. So one is that they are always at least weakly increasing. Okay. PDFs can, as long as the area under them is 1, PDFs can have really kind of any shape you want. They can go up, they can go down, but CDFs always kind of look like this. Okay, they have to be at least weakly increasing. And the other point I want to make about them is that CDFs eventually reach or approach 1. Okay. So as you're increasing B here, this is my B, and what I'm graphing here is the probability that X is less than or equal to B. That can't get smaller, right? As B itself increases, we're getting the probability of events that always incorporate the cumulative probability for lower values of B. Okay, so no decreasing ranges with CDFs. And at some point, that CDF has got to be getting really close to 1. Okay. Some CDFs will reach 1, others will just asymptote there. Okay, so segueing into the next 2 lessons, we can actually think about CDFs for discrete random variables as well. It's not quite as urgent for them, but that is what we're going to be doing in the next 2 lessons. So just thinking about what we're doing more generally, finding the CDF of X, it's always equal to the probability that X is less than or equal to B. And when X is continuous, it's just what I said before. It's the integral from negative infinity to B of the PDF of X. That's for X that's continuous. But if X is discrete, instead of a continuous sum, which is kind of what an integral is, we have a discrete sum. Okay, so the CDF for a discrete random variable is the sum for I less than or equal to B of the probability of those I's. Okay, so if it's a binomial random variable and you want the probability that X is less than 3, well, it's the probability that X is 0 plus the probability that X is 1, 2, and 3. Okay, and so you just literally are summing up the probabilities for all of the discrete values that are less than the one whose cumulative value you want. Okay, so I'm going to, we are going to find a discrete CDF in the next lesson, and then the one after that, find a continuous CDF so that you can just get a sense of the concreteness of what's going on when we find these cumulative probabilities.